Chapter 10, Part 2, the gas laws. So in this section, we're going to think about the laws that govern how gases behave. So in the 1660s, many things were noted about gases and their behaviors. These trends lead to the laws that describe the behaviors of gases: Boyle's law, Charles's law, and Avogadro's law. Together, these three are going to combine to form the ideal gas law. And so, in order to think about the ideal gas law, we need to think about how gases behave. So it was the first relationship, Boyle's law, is the pressure-volume relationship. This determines or realizes that the volume of a fixed quantity of gas at a constant temperature is inversely proportional to the pressure. So what does that mean? That means that the volume is equal to a constant times 1 over P. So the pressure doubles if the pressure doubles, the volume decreases. By half. So we can think about the fact that the pressure times the volume equals a constant. Now you may be starting to think, like, what does that constant mean? But basically, if in a closed system, so we're not changing anything, it's all the same, if you increase the pressure, then the volume of the gas is half. So the next law is Charles's law. We're going to think about temperature and volume. So the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. So it's important to note, at constant pressure is directly proportional to its temperature. Basically, we can observe this in a balloon. If you have a balloon and you cool it, the balloon shrinks. If you heat it up, it's going to get larger. So we know that the volume divided by the temperature equals a constant. And so this basically tells us that if the temperature increases or decreases, we will see a change in the relationship to volume. Using this information, it allowed us to determine the discovery of absolute zero, or 0 degrees Kelvin. This is the temperature where a gas should have no volume, 0 volume. It's been totally compressed. So we know this. So we know that to determine the temperature in Kelvin, it's the degrees Celsius plus 273.15. That value here is absolute zero. There is no temperature below negative 273 degrees Celsius. And so you could extrapolate to that, but that temperature doesn't actually exist. So that would mean that you basically have compressed the gas so much that it doesn't exist. So absolute zero came from Charles's law. Those two things and the Kelvin scale are intertwined into these gas laws. So the next law is Avogadro's law. It's the volume moles relationship, or the volume quantity relationship. So this tells us that the volume of a gas at constant temperature and pressure is proportional to the number of moles of the gas. So the volume divided by N, which in this case is moles. So N equals moles. In this case is also going to equal a constant. So if you increase the quantity in moles under the same pressure and temperature, then it is going to be twice as much volume. Now keep in mind, if you're thinking about this, the V over N equals a constant works as long as the temperature and the pressure are not changing. And so if those are changing, this does not work quite as well. So together, if we want to think about this, we basically can say that PV equals a constant. We know that V over T equals a constant. And V over N equals a constant. So these three laws, you can basically combine them together to give you PV equals PV over NT is equal to a constant, which we have labeled R as the gas constant. And so R gives us the equation we're likely a little bit more familiar with of PV equals nRT, where we have pressure, volume, moles, gas constant, temperature. And so the gas constant comes in a variety of different values. And so the gas constant that I tend to think about is R equals 0.08206 liters, atmospheres, mole, Kelvin. Some of the other R values would be that R equals 8.314 joules per mole, Kelvin. It also equals 1.987 calories per mole Kelvin. You could also get it in the units of meters cubed Pascal mole Kelvin. And in that case, it would be 8.314. And the last value would be 62.36 liters torr mole Kelvin. Now, as we look at these 5 different values, it's important to note that the units are different. So when you look at these equations, it matters what the units are. So I think it's really important to say, think about the units. The R value you need corresponds to which of these you have. If your pressure is in atmospheres, you could use the first value. If it's in pascals, you could use the third value, etc., etc. So we can kind of think about these in different ways. So let's look at using this in an example. So a scientist is adding chlorine gas to their reaction through a balloon. So how many grams of chlorine gas are contained within the 347 milliliter balloon at 36.2 degrees Celsius and 1.134 atmospheres? The first thing I like to do is to write down what I know. So we know that the pressure is 1.134 atmospheres. The volume is 347 milliliters. I'm going to convert that to liters because most of the options require that information. So we have 0.347 liters. The temperature is 36.2 degrees Celsius. All of these require us to convert that into Kelvin. So 36.2 plus 273.15, and that gives us 309.35. We're going to use the PV equals nRT. We're going to solve for grams, but grams are required to come from moles. So we're going to solve for N, and N equals PV over RT. And I'm going to use R equals 0.08206 liters, atmospheres, mole, Kelvin. So now we can basically plug this into our calculation and see. So if N equals the pressure, which is 1.134 atmospheres, times 0.347 liters, divided by R, which is 0.08206 liters, atmospheres, mole, Kelvin. And the temperature is 309.35 Kelvin. So when we plug this into our calculator, we can determine that there are 0.015506 moles of chlorine gas. Now we need to convert that to grams because that's what it asked for. So in 1 mole, there are 70.90 grams of chlorine gas. And when we plug this in, we get 1.09937 grams of chlorine gas. Now, we need to revise our answer to include the significant figures. So when we look back at the problem, we have 3, 3, and 4, which means our answer needs to have 3. So when we pair back our value, we notice that it's 109 and the next digit is a 9. That rounds up to 1.10 grams of chlorine gas. So let's look at another example. In this case, calcium carbonate, or CaCO3 solid, is the principal compound in limestone. It decomposes upon heating to calcium oxide and carbon dioxide. A sample of calcium carbonate is decomposed, and the carbon dioxide is collected in a 250 ml flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres at a temperature of 31 degrees Celsius. How many moles of CO2 gas were generated? So the volume is 250 milliliters, which is going to be 0.250 liters. The pressure in this case is 1.3 atmospheres. The temperature is 31 degrees Celsius. So 31 plus 273.15 equals 304.15 Kelvin. So we are going to again use this equation, PV equals nRT. We're going to solve for N, which is PV over RT. So I'm going to say that the pressure is 1.3 atmospheres. The volume in this case is 0.250 liters divided by 0.08206 liters atmospheres mole Kelvin. And then we're going to multiply that by the temperature, which is 304.15 Kelvin. Now you'll notice that I always write out my units. This helps me make sure that they all cancel out. So the liters and the atmospheres cancel, the kelvins cancel. And so this will give us an answer in moles. From here, we can plug this into our calculator and we'll get that 0.013 moles of CO2 are produced. And based on the equation, we know that this is the right number of sig figs. We could solve for any of these values, PV, pressure, volume, moles, and temperature, using the same format. So your best path forward is to write down what you know, get them all in the right units, and then start to plug them into these calculations.